Good morning, afternoon, good evening, everyone around the world. So my name is Mohamed Kassem. I'm going to talk today about just a general overview of what we think about open source chip design and its ecosystem. I will actually, because of the tight partnership with Google and the foundries, you will find some overlapping themes as I go forward. And so I will hover on them just with a little bit of repetition. So, so first, my name is Mohamed Kassem. As I mentioned, my background is hardcore chip design. I was involved in, I was working with Texas Instruments, responsible for developing the analog on the phone processors, and mostly for Nokia devices before the year 2007. And after that, working on all the analog, again, related to phone applications processors for phones like Motorola and the initial devices from Amazon, etc. I also have a hobby in general of making and breaking and looking at into things. And I have my own repository of teardown, uncommented yet, but buying things and actually digging through them, so which is a continuous hobby that works together with what we're doing. So I'm going to jump right into it. And so today, and as we go forward, after the smartphone came up, and now every single feature that we could imagine is in the smartphone. There is a whole direction of taking the smartphones back into different pieces in the different applications inside the world. And these applications vary in different industries, and they have their own needs. And the way we express these needs, we call them the long tail needs, which is the products that actually are applications that have a need for low volume, not as much as the smartphone, the millions and tens of millions, hundreds of millions of units. Now you're talking about a smaller number of units for a specific application, but the standard parts do not meet the needs for them. And that means it is best to actually have the right size right sized power and compute. So you need a little bit of optimization, which requires customization or custom ASICs. However, the expression custom ASIC is unreachable in terms of because of the concept of making a custom ASIC is kind of a distant because of the cost associated with it, the minimum cost, and the knowledge. So, and the availability of people who actually can do it. So if you think about this long tail, the yellow or the orange part of this chart, if these are tens of thousands of products and they need custom chips, first of all, you need people to do it who know how to do it. And the second one, you can use automation sometimes, but also most importantly, you need to reduce the cost so that it makes sense economically to get there. So this is going against what's happening in the industry today. I call it the effect of, you look at the sun, you don't see the stars. That's true, because most of the semiconductor industry news and advances they're looking at the most advanced technology nodes. You hear the 3 nanometer, the 2 nanometer. You don't hear any other areas because they don't sound as cool. However, the effect of that is that you can see the technology nodes are going down in terms of features. The cost is exponentially going higher, and the number of people who can actually afford that cost goes down, and then that means that the people who are capable of inventing and coming up with new ideas is just going down, and which is against the need of the industry that I saw earlier here, and also against in general innovation. And I always give the example of car companies. If someone anywhere in the world has a new innovation in car engines, or they just think of the chances of how much that a new innovation can make it in one of the car's mainstream manufacturers. It's very slim. And it requires a major undertaking that prevents it's prohibitive for a lot of people. So in order to do that, we need to do what I just said about the meeting the demand. We need a large number of people. Well, it doesn't work with this type of trend, so we need to change that trend. What we do, or what we needed to do, is to simplify the process and making it available for everyone for making chips. So, and also, that implies also the scale that Johan was talking about earlier. Everyone, think about it this way: if we simplify it enough, the number of people will increase. And the way you want to relate to this, to how do we simplify this? Think about what is actually holding us back is the knowledge, the technology, and the cost. So if you think back before, for those of you who actually can think of a world before the app stores, which is pretty much before 2007, before the actual, the iPhone kicks off and becomes, available. What if someone wants to build a software product that serves the market, helps somebody to do something, whether it's it's useful in one way, regardless if it's a game or some application that does some sort of a productivity function or so. So if you think about it, in order to create a software product and sell it before the app stores, it's a major undertaking. You don't know where you're going to sell it. You don't know how to get a customer. You may not know who else you're going to work with to actually make that happen. When the app stores showed up, what happened is it started from a point that's not zero. They connected people to the customers, and they created a structure so people can actually develop and deliver something called the app. So what happened is it converted the industry from thousands or hundreds of thousands into millions of people that are capable of building apps and sharing them with customers without actually having to be to start from scratch or take the risk that much to building something. And that actually includes kids. So that means a simplification got into this, got into the to the level where kids can actually do it. So if you think about the concept applied, the same thing concept in the chip design, it is actually possible, except you need access to have the design tools in a PDK, business process, and customers. If you do that, you can get it to millions. Okay, so how do we do that? So and you imagine a world in a case where if people can actually collaborate in a way that you can imagine the universities with with industry, with manufacturing, with testing, with software development, all of that in a way that they can actually communicate and work together. Back to stressing on the marketplace. So if you think about it, we want to see a world where people are capable of developing chips and putting them to the users of I call them here customers, but they call them people who need chips. And then on the other side, people who need chips can request and actually define chips that they want using or building on that ecosystem. Now, back to how do we do this? It's a little bit hard. It's not one company that has everything. You need at least these 6 sides of the AND gate, and I'm putting it explicitly here in an AND gate to show that it's actually, if you don't have any one of these, you don't have anything on the right. So, and we all know, the affordable manufacturing, the PDK, the tools, the IP, and then the knowledge. And then after all that, what does the market need, or who needs it? Today, there are partial solutions. You'll find different providers like, your practice, Moses, CMP, and others in the world. They try and they did a good job in providing some of the infrastructure, but it's still not as complete as possible to make it available to everyone. What we need is a complete solution for this, and we address every one of these arms in the AND gate with different ways, and without having to read these things, a small text. You can read it later, but I will, this is general representation that I will cover that all in the coming slides. So how to simplify the chip design in general, starting with then open access to the PDK. This is Yohan mentioned a little bit about it, but today, if you think about it, the PDK is the process design kit, and this process design kit allows the designer to use the technology and understands what the technology is capable of. Several efforts have gone around, and then the result is the following. There are 2 process technologies on the left here, the 130 nanometer from Skywater, 180 nanometer from Global Foundries, and then coming in the near future, it has been announced, actually, maybe I'll put the link later, that the US government is actually funding an open source process for fully depleted 90 nanometer process, fully depleted SOI process. Now, no NDA, it's open source. If you go to this link on GitHub, you'll find links to for the first 2 available with the SPICE models, the libraries, the IOs, the rules, everything that's under the sun. Now people say, well, these are old processes. They're not as cool. They're not as I mentioned earlier, they're not the sun, they're the stars. Well, let's just roll back the reality of the world. The fast, the Intel, when they developed processors back in the day, they had the Xeon processor developed on 180 nanometer and at 1.7 gigahertz speed. Yeah, people argue it's a custom design, custom this and that, but the process is capable. Just the way how the designer uses it makes a big difference. And if you look at the world, this is a representation that I got from the Euro practice team, and it is showing their slice or their the division of the usage of different process technologies. You'll find that about half of the slice is above 90 nanometer. So the process is still relevant. It's just not making it. You have to look at it with at night to see the value of these processes and where they apply in many products. For examples of these, you can actually just go to efabless.com/projects, and you'll see examples of them. When you've seen this slide in a different way with Johan's, what's important here about highlight is that and I want to use the word viral. So it did, because there was has never happened in the industry. In the year 2000, June 30, 2020, Google released that first PDK, the 130 nanometer from Skywater. It shows just how much the world wants this. It gets downloaded about 600 times a week for the last 2 years. This is an amazing number. That's no foundry has imagined that this would happen. So now that means that people are interested. Now, how many people design? It's a ratio of that, but we'll see. So the Slack environment, actually, this is another thing, is that the value of this, aside from the numbers, is that imagine that if you are used to chip design, that the things that you communicate about, asking about spice models, capturing something, talking about the rules, talking about anything that used to be confidential, you can actually talk about it in public and ask questions, and you can Google it. This is also something that's never happened. So we're actually pushing that stuff into Google so that it can be searchable and accessible through similar to the software world. Second thing in the design simplification I mentioned is the EDA tools. So the EDA tools are range. So there's we're used to the industry standards tools that are actually driving a lot of progress in the semiconductor industry. But excuse me. There is a need for opening the funnel widely. So by using open source engines to assemble open source EDA tools allowed ubiquity, where everybody can have the access to a tool to design something with a real process without having too much trouble. So Yuan mentioned this in one line. I'd like to elaborate on this. So when we built the open lane flow, the discussion with the Google guys were, we're software guys. We don't know what a DRC is. So I want it to look like a GNU compiler, even if it's bigger area or bigger or lower performance. If you think about it this way, and you actually consider it like a GCC, what happens is you open the door for 1,000 more X, people who don't have the knowledge or not need to know the knowledge for getting the chip on the back end of the site. I need to focus only on the function of the chip, which is I can describe it with a hardware description language. So this is a unique part. It's against the fabric of the notion in the semiconductor industry that you have to optimize everything for lower cost and higher performance, because the process is so expensive. But if you unlock that and you go to a process that is less costly or cheaper, you'll end up with, yeah, this actually makes a lot of sense. We also have the tools on the analog space. So they're available to, you can actually use this. And thanks to the community members around the world, in order to enable that to work, people are actually collaborating openly. They're not even a part of a company. So why is it important to have the tools open source? Is that it again limitless availability. If you have an idea, you can just jump and try it. You don't need a permission from anybody or pay a single penny to anybody. And then obviously the collaboration. Number 3 is that not start from zero. So one of the things that we worked with is to build a chip that is not complete, that has, call it the 15th floor, and then you add your own piece on top of it. So you don't have to build the whole chip from scratch. So in this case, there's a chip called Caravelle. That chip has resources available, like a 32-bit microcontroller, logic analyzer, and a variety of IOs, and it's standardized interface. So the designer needs to, if whoever they are, if you want to design something, you can start from scratch, but also you can start from that chip with the this 10mm square area, and then you focus only on one piece, which reduces the knowledge needed to develop the whole chip. You need to focus on what you have there, and you could you don't have to have the knowledge or the time to develop a complete chip within the design period. Last thing you get is you get a board in your hand. This board is actually, this is the real board here. So you get that board, you plug it into the USB, and you can actually get the chip to be up and running without actually having to change much by preparing it work. All of this because of the standard interface of the chip. So, and then obviously you because of the resources on the chip, you can do a bunch of things, and you get enough parts that you can play with them. You can also develop your own board. So the cycle would, in full would look something like this, that you get the tools, you get it. Now, using proprietary tools is open. You can use it from, you can use your own tools, you can use any tools, as long as you design that piece. So this is not just about open source EDA, it's also about open source design and how that open source design can be created through whatever means available. The other thing that simplifies, and I mentioned in the AND gate, is that you need blocks, you need functions. So these functions, we need an open library. So then if you look at what's happening now since the year, since June 2020, the community has developed hundreds of designs available to with code and simulation and layout and schematics that can be actually used. Now, we have kind of a work to do to get actually to that, what I'm describing here on the slides, where silicon proven, highly high confidence verification was applied to them in a way that use them as building blocks. But if you think about it this way, think about the software, where you can use libraries from the software open source community that have been heavily used by other people that can be reused within the design. And again, if you go to efabless.com/projects, you'll see examples of this. And again, as I mentioned, the maturity and the quality and the completeness of the projects depends on which community and who did it. And this is something we're all working on together as a community to bring up the robustness of these projects. There has been a roadmap, and I think it's covered in the previous presentation a little bit, but we try to, as much as we're talking about the process and the process more roadmap, we want to actually escalate and go and try different things, try different processors, different analog, different ways of building analog, different. So, and engage that in the way that, engage the different efforts in a way that everyone would contribute with their own strength and expertise. So, the open source chip design in general is useful for multiple things, but the most important part of it is is security by transparency. Is that this is an example that NEC worked with eFabless, is that for some chips, is that when you have them open source, you can actually inspect them for for Trojans and backdoors, and use it for authentication. What's called the root of trust. One example of that is something like OpenTitan from Google, but it is, if OpenTitan is on the left, now if you go to the right-hand side of the red column here, that means it's actually possible now to build a full stack and have an open source security chip, which is inspectable and confirmed. It doesn't have open doors. This is just an outside data point. I just wanted to mention it, is that open source design, it's not just about open source and collaboration. It also has an incredible commercial and value, has to do with the security. So examples of other chips, and I'll hover through them. These are all of them built with open source tools. And the example, one of these chips is called Raven. It has been designed with a mix between open IP and closed IP. So It was actually, you can mix, you don't have to have app, all of them are open at the same time. So now the cost of manufacturing is something that is hard to overcome because it's physical material. It's not just about time or somebody can reduce it. So if you think about, again, the general process of learning, whether it's in software or otherwise, it's about design, test it, learn from it, repeat. Design. Now, this is an expensive process if you do it on chips. So this is where the Google program came, Open MPW program came on in the picture, where it covers that part about the cost. And Google provides and supports 4 manufacturing runs every year for one process. Right now it's 130 nanometer, and this you'll see the Global Foundries 180 nanometer, and then in 2023 you will hit the 90 nanometer. Most important part of the Google MPWs here is that there's no other criteria for selection other than that you have it's a lottery, and the lottery doesn't care about who designed it, as long as the design is manufacturable and it is complete from a manufacturing standpoint. It can pass that filter. It is in with the bias towards the submission early. So if it doesn't matter who you are, if you design something and you put it on the Google shuttle, the earlier you put it, the higher chances that you can get it in, and that Google pays for the manufacturing for you. And there are several examples of the previous ones, and Johan covered a bunch of these already. So in terms of the who and what they did, who was on the chip on the shuttle, and of course the key point here is to mention is that because of the simplification, more people that didn't design chips before coming from embedded hardware development or FPGA world, they're actually, or even examples from the software world, actually started to materialize and do their work on chips. And this was actually just a milestone. It's never happened before, but now it's the open source hardware has been etched in one of the chips, and it is a bit, this is, again, history in the making in that case. There are so many contributors and people who got engaged and tried and used it, companies or universities. The number of projects, the Google projects have 40 runs per shuttle, 120 per year. So the last year we had 4. So there's always, it's over, the 40 is always full and overflowing, so overbooked. So it is going forward. It shows the traction and complete and total traction and interest in the community. So of course the community at work, they do interesting things like, this is an example of a community member who provided a complete test setup for an SRAM chip with temperature control. Another one built, this is one of the students, they built a complete DC-DC converter, switching regulator, buck. Then this is an example of work we've done with Stanford University in one of their courses, and where we had like a bring update. Chip that I'm portraying here, our friend Tim Edward, of just taking pictures. He's done a lot more than that. So yeah, he's been the key driver for this project in many ways. And then NIST was mentioned. Again, that's a community. NIST is an organization that's doing high temperature or low temperature characterization at 4 Kelvin for some of these devices that we're open source. Last thing is that I want to just hit on is that we think that this is going to get into, I want the simplicity will get down into the level of Arduino and Raspberry Pi. Think about that you can actually use a graphical interface to generate that user project, and you can actually have your own chip done like this. This is a very important piece of the picture, is that as we go forward, the structure, the way the chips are being made can be abstracted, and they are chips. They will have functions. It will serve that many people will actually be able to get the feeling of what my own chip and do it and move forward with it in a way that removes intimidation. So people usually think it's a hard thing to do. It is a hard thing to do, but it's like driving a car. Well, do I need to know everything about the car to drive it? Well, there's an interface, and that interface is unified even across electric and non-electric gasoline-driven or powered cars. So I'm gonna, in the interest of time, I'm gonna just stop here and then share just a slide with links that the user or the team or the audience can actually take a look at, and then we'll answer questions after the workshop for anything related to this topic. Thank you.